So we are all familiar with some successful applications of natural language processing in English. For instance, we can now generate high-quality translations in French, or transcribe speech signals in English to text, or answer factual questions. And all these successful applications have been possible because we had generous amount of supervision available for these tasks, either in the form of millions of lines of parallel data, or hours of transcribed text, or thousands of question-answer pairs. However, if you are working with a language other than English, such as Amharic, Urdu, or Hindi, you will have to deal with the challenge of working with limited or less supervision, and that is going to be the theme of today's talk. In today's talk, I'm going to discuss two different approaches by which we are going to address these challenges. In the first part of my talk, I'll talk about how, by exploiting supervision for the same task in other languages through a shared feature space, we will learn better models that generalize well. And in the second part of the talk, I'll describe how we can compensate for the lack of supervision by using additional knowledge and lots of unlabeled data to drive the learning. And in particular, I'm going to examine these approaches in the cross-lingual information extraction setting. So I'll examine two problems, cross-lingual entity linking and low-resource transliteration. And both of these works appeared in the recent EMNLP. All right, so before I begin, I just want to highlight some of my previous work in cross-lingual language understanding. In the first part of my thesis, I worked mostly on lexical semantics, or understanding the relationship between words in different languages and how we can learn or identify these relationships and use them for downstream tasks. And more recently, I have focused on using these representations for doing downstream tasks in information extraction, and that is the focus of today's talk. All right, so let's start with the first part. I'll first briefly motivate and define the task of entity linking. So suppose an NLP system was reading this tweet. Jay Cutler passed his physical and is officially a dolphin. Now, there are some spans of text in this tweet that refer to entities. And if you look at the word dolphin, it can refer to multiple entities in any knowledge base. However, we as humans can appeal to some background knowledge and realize that dolphin here refers to the Miami Dolphins football team and not the aquatic mammal. And this task of grounding spans of text to a knowledge base, or to an entity in a knowledge base, is entity linking. And grounding early in the conversation also helps you later on. So suppose someone replied with a tweet saying he used to be a bear. Again, bear is ambiguous, but the fact that we grounded Jay Cutler and dolphin earlier helps us to realize that bear here refers to the Chicago Bears football team and not the mammal again. So entity linking helps you to augment your text with some background knowledge so that you can perform downstream NLP tasks which require reasoning, such as relation extraction or question answering. Cross-lingual entity linking is simply the cross-lingual version of this task. So you're given a piece of text in a foreign language. For instance, here it's in Tamil, a language spoken in India. The translation is shown right below the text for your benefit. And the task is the same. You want to ground spans of text that refer to entities to a knowledge base in English, like Wikipedia. And this task is challenging, firstly, because you have to deal with ambiguity. You don't want to link to Suarez's elder brother or the University of Liverpool instead of the football club. And there's an additional challenge. Because this is a cross-lingual setting, you'll have limited supervision. And to appreciate that, let's take a quick detour and see how entity linking is done in English. So in English, we have lots of linked mentions of an entity like Liverpool that all point to the football club's Wikipedia page. And using the contexts of these linked mentions, we can learn some form of context representation that can accurately disambiguate which Liverpool is being talked about. And this is possible in English because English has lots and lots of linked mentions available as supervision. So if you look at the English Wikipedia, you'll have more than 50 million linked mentions. However, if you go to the Wikipedia for a language like Tamil, you'll have orders of magnitude less supervision. And this was the problem of working with less supervision that I was alluding to earlier. So how do we get around this problem? So the solution becomes evident if we look at things from the perspective of a single entity. So here is the Tamil Wikipedia page for the Liverpool Football Club. And as I said earlier, you'll only have a handful of linked mentions. But if you go to the English Wikipedia page for the same entity, you'll find out that you have lots and lots of linked mentions available as supervision. So this naturally suggests that we should try and combine these two sources of supervision somehow. And we could do this if we can learn some representations that capture or preserve the semantics of an entity across languages. Any questions so far? Okay. All right, so we already know how to learn representations that capture the semantics of words across languages, namely via the medium of multilingual word embeddings. So these embeddings encode a discrete translation dictionaries in 2 or more languages, such as the one shown here, into a vector space, such that words which are translationally equivalent cluster together in high-dimensional space. So for instance, all the words which are translationally equivalent to market are clustered together, and so on. And our idea is that we are going to use this as a building block for our shared feature space to combine the supervision. More formally, the idea is to combine supervision in a high-resource language like English and a low-resource language like Tamil by first encoding the words that appear in the contexts of these mentions by projecting them through the multilingual embedding space into a shared cross-lingual space, and then learn the context representation that we'll use for entity linking on top of this. And in our model, we are going to achieve this by what we call the mention context encoder. All right, so let's see what this mention context encoder does internally. So the mention context encoder operates on 2 types of context defined by the mention. So if the mention is Liverpool, we'll have what we call the local context, which is the lexical neighborhood of the mention defined within a small window around the mention. And we'll also have the document context of the mention, which is the surfaces of all the other mentions that appear in the same document. And as I said earlier, the tokens in the local context will get projected first by the multilingual embeddings. And on top of this, we have a local context encoder, which is simply a convolution operation with some average pooling on top that generates a dense local context vector C. And similarly, the document context will get encoded into a dense document context vector D. And finally, both these 2 representations get combined to form a mention context vector G that's going to be used for disambiguation. All right, so besides having the mention context representation encoded by the mention context encoder, the model also maintains representations for each entity in the knowledge base. So for instance, you'll have a representation for the football club as well as a representation for the city. And the idea is that to facilitate accurate disambiguation, we want to ensure high similarity between the correct entities vector and the context vector that is generated by the context encoder. And to ensure this, we can define a conditional probability distribution, which is the probability of linking to a given entity given the mentioned context, which is M. And this can be defined to be the function of the similarity of these 2 representations. And at training time, what we can do is we can maximize the log likelihood of this conditional distribution for the correct entities. And for that, we can define an appropriate loss term, which I'm going to denote by the EC loss. So this is entity given context loss. All right. In addition to this, both these representations also take part in a different task, that of predicting the fine-grained type of the relevant entity. So for instance, one of the fine-grained types of Liverpool in Freebase is the sports team. And again, the rationale here is that by doing this additional task, we will force the mentioned context representation and the entity representation to score entities of the relevant type higher than the others, and hopefully this will improve the disambiguation performance. And again, for both of these edges, we can define appropriate loss terms. So the TE loss is the loss for the problem of predicting the type given the entity, and likewise TC loss is predicting the type given the context. And at training time, we can simply optimize a linear combination of these three losses, and that's the model. Any questions so far? Yeah.
How many possible entities are there when you're doing this?
So we work with around 500,000 entities from Wikipedia. Okay.
So is there in this, you didn't give the formula for the last, but is there some notion of negative examples or some sums you have to calculate over all the alternatives?
Right. So I'll discuss what are the examples that compete against the gold in the next slide, actually. Yeah. Any other questions? Okay. So suppose you have trained this model. How do you perform inference? Well, so you don't want to score all the entities in the knowledge base because that would be impractical. So first, we identify a small set of candidate entities that a given mention can link to. And we do this by exploiting the interlanguage links in Wikipedia. So the idea is that given a mention in Tamil, which is the string Liverpool, we first look at all entities that it can link to in Tamil Wikipedia. And for each of those entities, we simply navigate the interlanguage links, which is a one-to-one mapping, to identify the corresponding page in the English Wikipedia. And this will give us a small set of candidates that we can ground to. And for each of these candidate entities, we compute what we call the prior probability of linking to that entity, given simply the mentioned surface. So you can think of this as some measure of popularity of that entity. So if that string refers to the city of Liverpool 40% of the time, that would be reflected by the prior. Now, this prior probability will get combined with the probability distribution learned by the model in the previous slide. So probability of linking to the entity given the context by some function f. In our case, we simply use union, but this could have been a learned function. And finally, at inference time, we simply take the argmax with respect to this small set of candidates for computing the prediction. So the negative entities would be simply the other candidates. Yeah. All right. So let's see how this model fares in the experiments. In the first set of experiments, first the evaluation datasets. I'm going to evaluate on two datasets. The first one being the dataset from Shyam Upadhyay. This was data derived from Wikipedia, and I'm going to report the results on these 8 languages. Shyam Upadhyay categorized the mentions into hard and easy mentions, and we are going to evaluate on the category of the hard mentions. Hard mentions are those for which the most probable answer according to the prior, so according to popularity, is not the correct answer. So, for example, this mention of Berlin, in this sentence, Terry Nunn left Berlin to audition for Star Wars. Usually Berlin would refer to the city, but because it's a hard mention, here it refers to the band.
What percentage of the full data set is that?
Pardon?
What percentage of the data set is hard?
I would say around 30% or so. It's because it's all derived from Wikipedia, and Wikipedia is predominantly easy mentions. So it's a small percentage, yeah. And The second data set that I evaluate on is the data set from the TAC evaluations. This was derived from news and discussion forums, and it's for 2 languages, Spanish and Chinese, and it contains a mixture of hard and easy mentions. Okay.
You also train on the hard mentions, or are you training on the standard distribution and testing on the hard?
The training is only done on the remaining mentions in Wikipedia. At test time, the model does not know whether it's going to get evaluated on hard or easy mentions, or a mix of both. Yeah. And in terms of the model variants, we evaluate 6 different model variants to highlight the benefit of different aspects. So firstly, the variants vary in the languages that they use for supervision. So we'll have a monolingual variant, which only uses the target language Wikipedia. Then we'll have a joint variant, which uses additional supervision from the English Wikipedia. And we also trained a multilingual model on 5 related languages, Spanish, French, German, Italian, and English. And these would be used for the relevant languages in the experiments. And for each of these variants, we also have the variant which incorporates the multitasking type loss to show if adding the type loss is helping at all or not. All right, so let's look at the experiments. First, on the European languages from the Sy and Roth dataset. Here I'm going to plot the linking accuracy on the y-axis, which is how often we predict the correct disambiguation. And on the x-axis are the various model variants and the previous state of the art. So the first thing that we would notice is that using the joint supervision from English improves significantly on the monolingual model. Another thing to notice here is that incorporating the type loss both in the monolingual model as well as the joint model improves performance. And in fact, we improve significantly on the previous state of the art, which was the Sy and Roth model itself. And another thing to compare here is the performance of the multilingual model with the joint model. So you can see that the performance only drops negligibly, and in fact, it improves slightly when we add the type information back. And this is really encouraging because now we can train a single model for 5 languages, which is a reduction of 5 times in parameter space.
Why are French and Italian so much harder?
Okay, so you really cannot compare these two in that respect because the data set was not controlled in that way. It just happened to be that the mentions that we test on French and Italian are harder than those in.
Oh,
But you cannot compare these two because when the test data was created, it was not it was not controlled for having the same degree of difficulty in across languages. Does that make sense?
Yeah.
Any other questions? Okay. A similar trend is also observed for the non-European languages. Again, the joint model improves significantly on the monolingual model, and incorporating the type loss improves performance. And finally, on the TAG data set, one thing that you would notice here is that performance improves significantly compared to the previous 2 slides. So in earlier slides, the performance was varying from 50 to 60, but here it's in the high 80s. And the reason for this is because it has a mixture of both hard and easy mentions. So the easy mentions inflate the performance. But again, you can see that the same trend holds here. The joint model improves significantly on the monolingual one, and adding the type loss helps here as well.
So I didn't see in your previous slide, but does the multilingual model help more with low resource languages than it does for high resource languages?
Sorry, but so.
Does the joint model help more with languages like Tamil and Turkish and Arabic than it does for, say, Spanish or?
So again, I think when you are comparing 2 languages, it's not going to be a fair comparison, right? So you cannot really assert that it's helping one language more than the other.
You could talk about relative error reduction.
In that respect, I think the low resource languages do get more benefit, but the reason for that might be because there might be less ambiguity in the low resource test data itself. because the low resource languages will have smaller Wikipedia, smaller number of entities, so it's a slightly easier problem. Does that make sense?
Yeah.
Okay, so moving on. A more interesting set of experiments is the one where you have limited resources in the language of interest. So in particular, what I'm going to do here is I'm going to gradually increase the number of mentions available as supervision in the target language on the x-axis and keep track of the performance in terms of linking accuracy on the y-axis. And I'll do this experiment for 3 languages, again on the hard mentions. This is Turkish, Chinese, and Spanish. So for instance, here is the performance of a model which is only using the monolingual supervision. So it only uses, say, 250,000 mentions to achieve that much performance. You can see that the performance is quite poor. However, if you compare this with the performance of a jointly supervised model, which uses additional supervision from English, you see a dramatic improvement. So compare the solid green line for Spanish with the dotted green line for Spanish. Another thing to notice here is the performance in the zero-shot setting, where you have 0 mentions, so on the y-axis. You can see that just by training an entity linking model in English and transferring it across languages via the medium of the multilingual embeddings, you can still achieve some reasonable performance, which is still better than the performance of the monolingual model. And finally, for reference, this was the best performance in the previous 3 or 4 slides for each of these languages. And you can see for languages like Turkish and Chinese, we are approaching the best performance pretty quickly, just with 1 million mentions or so, which is, again, very encouraging.
How do these models scale in terms of like top K accuracy? Like, for me, I kind of think of entity linking model, which is 45% accurate, is essentially unusable.
Mm-hmm.
But depending on if the top 3 accuracy is in the like high 80s.
So again, this depends on language to language, but I would say that as long as the gold candidate is somewhere in the top 5 or top 4, it's very plausible that you will be like 80% accurate on that. But beyond that, it becomes even more harder. Yeah. So definitely, like on the hard mentions, the ceiling of performance is definitely not 100%. There are some hard mentions which are extremely hard. You have to go deep down the candidate list. Any other questions? Okay, so let's finish the first part of this talk. The key takeaways from this section was how, by jointly utilizing supervision across multiple languages, we were able to generalize better. Another thing that I showed here was by using metadata like the type information to do multitasking improves the entity linking performance. And finally, I showed that in a limited resource scenario where you have only a handful of mentions to supervise with, using joint supervision is almost always crucial for getting good performance. All right, so the story so far was about grounding mentions expressed in different languages into a knowledge base in English, like Wikipedia. And to achieve this, we exploited a property of the Wikipedia, which was that knowledge about the same entity is expressed in multiple languages. So there's some redundancy across languages. You have information describing the same entity in multiple languages, and these information sources might be disjoint, or they might have some overlap. This will not always be the case. In fact, you'll have knowledge bases in which you will not have this redundancy, and information is only expressed in one language, which will mostly be in English. So here are some examples of such knowledge bases. Your knowledge can be expressed in a database of, say, restaurant names, reviews, and their timings, or it could be expressed in a relation graph of medical entities and the relationships between them, or it could be simply a table or a list. And in these cases, we would still like to be able to field queries that are posed in other languages. So for instance, you can have queries expressed in Hindi, Tamil, or Russian, Again, the translations are shown below each query for your benefit. And again, to answer these queries, you need to be able to ground spans of text from the query into the knowledge base, which is expressed only in English. So for instance, to book the table at the relevant restaurant, you first need to realize which entry in the database is being talked about. And in all these cases, it's not that the disambiguation problem is hard, but actually identifying the plausible entities that you would want to ground to is the hard problem. And it's hard because identifying the entities requires you to compare names that are written in different languages, in particular, different writing scripts. And this motivates the next part of my talk, which is about doing transliteration of names. In this task, the idea is that you want to rewrite a name that is written in a certain writing script, like the Hindi, Tamil, or Russian writing script, to a target writing script, which in our case would always be in English. And the hope is that by performing name transliteration, we would be able to identify candidates even if our knowledge base is only expressed in English. All right, so first of all, you might be thinking, is this really a hard problem? Why not develop a rule-based transliteration system which looks at each character individually, and we can probably work with that directly. So here's an exercise for the audience. These are some names, some Western names, which are written in the Bengali script. And here's the output of a rule-based transliteration system for each of these names. I request any Bengali speaker in the audience to refrain from answering. So the task for you is identify as many Western names as you can. It will require a bit of squinting. Okay, Robert. It could have been Roberta as well, but sure, Robert.
Is that Brangelina?
No.
Is the first one Winston?
The first one is Winston, correct?
Franklin.
Franklin. If first one is Winston, this would be, okay, Churchill. Winston, Robert, Franklin, Churchill. What about
Harvard?
Howard, right? The last one is probably slightly hard. That was Rhodes. So for comparison, this is the output from a learned transliteration model. And you can see that you don't have to squint that much, except for probably Churchill. And hopefully, this would convince you that if you're going to use the output of transliteration in a downstream NLP system, you don't want to use a rule-based system just because it's going to be so noisy. All right? Okay, so let's see how people have tackled the transliteration problem in the past. So there have been two threads of work on doing transliteration. The first one views transliteration as a generation problem, where given a string in the foreign script, you can think of this as doing translation, but where the words are the characters in the word in the input word. So you can use any of your favorite statistical machine translation approaches to generate the correct transliteration. The second approach treats this as a discovery problem or a re-ranking problem, where given the input name, you want to find the appropriate transliteration from a predefined list of names. And again, it's obvious that this will have some issues with coverage. If the correct transliteration is not in your predefined name list, you will never find the correct transliteration. All right? And for this reason, the focus of this work was doing generation, specifically generation in a low resource setting. However, we are still going to exploit one fact about discovery, that discovery is a considerably easier task because it has a restricted search space. And we are going to use this later on to benefit our generation model. Okay, so we're going to make an assumption. We are going to assume that transliteration is a monotonic sequence generation problem. And what I mean by that is, given a sequence of characters in the foreign script, the characters in the English script will be generated in a monotonic manner. So for instance, a generation like this is not monotonic because you will have crossing edges between the characters that are being generated. And the rationale behind having the monotonic assumption is that when you're rewriting a name in a different script, you would ideally want to preserve the pronunciation, but if you destroy the monotonicity in the generation, the pronunciation would not be preserved. Now, you can see that in this picture, the alignments are actually not provided to you as supervision. These would be latent. The only thing that you have is the name pairs. However, these alignments are useful because they describe how the generation process should proceed. And for that reason, what we are going to first do is we are going to first infer some of these alignments by using a process like EM and ensuring the monotonicity constraint and infer these alignments from your name pairs that are provided during training.
Sorry, what was the motivation for why the alignment should be monotonic?
So if you have non-monotonic generations, your pronunciation, the same name will get pronounced in a different way.
Why would I not expect that to be different?
Well, okay, so transliteration would be largely monotonic because if you destroy the pronunciation of the name, then it's difficult to recognize the same entity, right? It's not going to happen.
The pronunciation is like as how it's spoken.
Right, because each character in the original writing script has a sound associated with it. So if you rearrange the characters in the target script, the sounds will also get rearranged. Does that make sense?
I mean, you could say empirically when words get transliterated into other languages, they tend to keep monotonic alignments back.
Right. There's an empirical motivation for having the assumption as well. Yeah.
Is there any exception?
Oh, yes. So there would be exceptions in, say, languages like Japanese. So you might need to, so for instance, in Japanese, orange juice becomes oranju jusu because you need to have.
But that's still monotonic. You're just inserting more vowels.
Okay, that's true. That's true. Okay, non-monotonicity, I'll have to think of a better example.
Just curious.
Yeah, there would be some exceptions, but there would be few, I think.
I think it's agreed they're rare.
Any other questions about this? All right. So as I said, we are first going to infer the alignments given just the name pairs that are provided as supervision. Now, how do we use these alignments? What we want is our generation model to enforce monotonicity when it's generating. So first, what we are going to do is slightly modify the sequence-to-sequence with soft attention architecture. And the idea is that we are going to bake the monotonicity constraint into the generation process itself. So the encoder remains the same as usual. We'll have a bidirectional RNN, which encodes each character in the input and generate hidden representation for each position. However, the decoder will, instead of attending to all positions, it will attend to a single position in the input. For instance, it's right now attending on H0. And the position that is being attended to will increment every time the decoder generates a special step action. So right now, the decoder has generated a step action. So we'll move on to the next position, which is H1, and generate a T, still attend on H1, generate a H, a A, until we generate the next step action. When we move to, and that's when we move to the next input character. And this way, proceeding as I described, we can transliterate Thanos written in Hindi into Thanos written in English. And because the motion of the step action is always either it's going to be at the same position or monotonically increasing, this will ensure that the generation will always be monotonic. Any questions on this?
Where does this step decision come from?
So the sequence of the actions that you need to take, the oracle sequence, it can be determined exactly from the monotonic alignments that we infer. So once you have these alignments, you can determine the exact sequence that you need to take, the sequence of step and generate actions.
So is this empirically true that these transliterations are monotonic within the model also just learn it anyways?
Right. So the premise is that we are working in a less supervision setting. So if you want the model to learn the constraint, you will probably need to pour lots of data for the model to discover the constraint. But if you bake the constraint into the model, you can get away with less supervision. Okay, so moving on. The natural question here, as you pointed out, is what happens if you don't have enough supervision? So the alignments that you infer would be noisy, and also your sequence-to-sequence model will not generalize better. And for this, we are going to exploit the fact that I talked about earlier. We're going to exploit that discovery is a considerably easier task. And in particular, we are going to use discovery to bootstrap our generation model. So for bootstrapping, we are going to use 3 ingredients. The first ingredient is a small training set of name pairs. The second ingredient is a list of names written in the foreign writing script. You can source this from a monolingual corpora in the foreign language. For instance, here are some names written in Hindi. And the third ingredient is a list of known English names that you can source from your knowledge base. For instance, you can source it from Wikipedia or any other knowledge base that you're trying to ground to. The first step in bootstrapping is to simply train a weak generation model with whatever supervision that you have. And using this generation model, we are going to generate some k-best predictions for all the words for which we don't have the counterpart transliteration. And then these k-best predictions are going to get matched against the known names in English via the medium of some constraints. And using these constraints, we are going to discover some new name pairs that we can add back to our initial training set. And this way, we are ready for the next iteration, and so on and so forth. And this way, by using the knowledge that is encoded in the knowledge base and some constraints along with some unlabeled examples, we were able to compensate for the limited amount of supervision and drive better learning. All right, so let's see how both the generation model and the bootstrapping approach work in practice.
Do you ever throw out those generated training if you, in a later iteration, you found out they were bad?
Okay, so that's a good question. So after you add new things and train a new model, you purge the set of discovered examples. So you will not get influenced by bad examples that you mined in iteration 2 in iteration 10. Okay, so the first experiment is the experiments in the full supervision setting, and here, this is to evaluate how good the generation model is. Here I'm going to plot the accuracy at 1 on the y-axis, and the different model variants are on the x-axis, with our model in both the unconstrained inference and the constrained inference setting. And this evaluation is on 5 languages with different writing scripts, so Bengali, Hindi, Kannada, Hebrew, and Tamil. So another thing to notice here is the inference strategies. So we will perform beam search with a beam width of 10. Either you pick the topmost item in the beam as your prediction, which is the unconstrained inference strategy, or you can exploit the fact that you have a knowledge base at your disposal. So after doing your beam search, you pick the first item in the beam that also appears as a name in your knowledge base. So that's the constrained inference strategy. So in the unconstrained inference setting, we improve on the previous works. And the main reason that we improve is because we have the monotonicity constraint baked into the model. I'm not going to go into the details of that. And again, for the constrained inference setting, we improve upon another approach which uses entity linking model to improve the beam search, to re-rank the items in the beam. And this is really nice because our constraint inference strategy is much more simpler. We don't need an entity linking model. We can just work with the names in the knowledge base to drive the constraints or to re-rank the items. So that's the story in the full supervision setting. The more interesting experiment here, again, is the low resource experiment. So here we are going to provide 500 examples as initial supervision to each model and track the performance after each bootstrapping iteration, again, in terms of accuracy at 1. So for instance, this is the performance when you bootstrap a model for Hindi. So with 500 examples, you have a performance of around 30% accuracy at 1. And after bootstrapping for 6 iterations, your performance increases by around 10 points to around 40%, which is pretty nice. And if you compare that with the model which is fully supervised, which has almost 20 times more supervision, you can see that we come pretty close to the fully supervised model, which is around 42 to 43% accurate. So this is also a really encouraging result because you can work with only 500 name pairs and bootstrap to a much more competitive performance. And when you plot the same curve for other languages, you find out that there's a similar trend. You get pretty close to the performance of the full supervised model in almost all cases, except for Kannada, in which I think the gap is around 3 to 5 points. But nevertheless, this is showing that bootstrapping really helps in improving your model. And as the final experiment in this part, we are going to examine what we started off with as the motivation for transliteration, using transliteration for doing candidate generation. And to remind you, okay, there's a slight delay. To remind you what the candidate generation problem was, you're given a string in a foreign language, and you want to identify candidates that you can ground to in a knowledge base in English, like the English Wikipedia. So in our experiments, we are going to use a simple baseline, that of doing a name match. So you have a lookup table of names and their corresponding transliterations to English. If you find a match, you can simply look up the correct transliteration and proceed as usual to generate the candidates. Of course, this will have coverage issues, so you might not find a entry in your lookup table. And in that case, you fall back to your generation model that I described earlier. And for this experiment, I'm going to use 2 slightly exotic languages. One of them is Tigrinya, and the other one is Macedonian. And the idea is that these languages have small Wikipedias, so the dictionary that you use for lookup will be considerably small. And this way, you can stress test your generation model. And in both the settings, we'll provide 1,000 name pairs for each of these languages as supervision for the transliteration model. And because we are evaluating candidate generation, the evaluation metric is now recall at 20. So how often is the correct candidate in the top 20 candidates? And as an upper bound in the performance, if you have a perfect transliteration system, you will get 60% recall and 80% recall in both Tigrinya and Macedonian. So the upper bound is far lower than 100% in both the data sets. And again, if you look at the results, you can see that just using the transliteration model or using the model with bootstrapping, we gain several points in performance over a simple name matching baseline. So this shows that if you use this the transliteration model for doing entity candidate generation, you will definitely improve. All right, so that concludes the second part of this talk. I showed today by how constraining your learning using background knowledge, you can compensate for the limited amount of supervision that you have. This was shown in the bootstrapping approach. We also saw how by incorporating the monotonicity constraint into the model itself, we were able to generalize better, even in a low resource scenario. And finally, I showed how by using transliteration, we can improve on downstream tasks like candidate generation. All right, so before I conclude, I would like to talk about some future directions. So today's talk was revolving around grounding multilingual text to some form of knowledge. And a natural future direction in this is to perform reasoning on top of both, on top of the information expressed both in the text and the knowledge. And this reasoning can come in many forms. For instance, it can be extracting new facts from multilingual news sources. So if a news source in Tamil expresses that Barcelona has bought Suarez from Liverpool, you can update the edges in your knowledge base appropriately. Reasoning can involve a more high-level task of doing entailment in a different language. So if your premise and hypothesis are both expressed in Hindi, and you want to know if one of them is entailing the other, we could probably do that. And an even more challenging setting would be when your knowledge itself is situated in a real-world scenario. So if you have a command asking to dispose the pizza that you ate last week, and you have a knowledge base which is situated in a scenario, you would like to ground some entities and generate an executable pass that you can then hand over to your personal robot. And again, there are many other forms of reasoning that you can perform in a multilingual setting. And the hope is that sometime in the future, someone would give a talk about learning and reasoning with less supervision in a multilingual setting. And on that hopeful note, I would like to conclude this talk and also thank all my collaborators. This work would not have been possible without them. Thank you.